Hello and welcome to JHEP's lesson on mechanisms suitable for all examples, especially F322. Well, the three things that we need to learn are the three types of mechanisms, which are electrophilic addition, radical substitution, and nucleophilic substitution. Well, the first thing that we should know is that alkenes go through electrophilic addition. Why? Well, we have got this electron-rich double bonds over here, which has got lots and lots of electrons, and those electrons actually manipulate diatomic molecules to become dipolar. So say for example we've got bromine. Bromine usually comes as a diatomic molecule because it's a group 7 and is usually neutral, so all the electrons are shared equally between them and so forth. So this electrons, as soon as it approaches this alkene and the electron-rich double bond, it actually gets scared. The electrons on this side kind of get scared and they move towards the end of the bromine. So therefore, this bromine at the top is slightly positive because we've got less electrons on it as before. And over here, it is now slightly negative because we have got relatively more electrons on its side. So what else happens? When this happens, the double bond over here is like, nice, because it really likes positively charged. Even if it's slightly positive, the electrons like positively charged stuff. So what happens is that the pair of electrons would transfer to the bromine, which is positively charged. Remember, we have to use a curly arrow to show the movement of electrons in the formation or in the breaking of bonds. So remember, when I just told you that definition, we said that there is going to be a bond forming made, so keep that in mind. The second thing that happens while these electrons are transferring, the electrons on the bromine get even more scared and they just move to the second bromine. And when that happens, it splits through heterolytic fission. Okay, where all the electrons that are being shared between the two bromines have now gone to one bromine, and this ends up as a bromine minus, a bromine ion. Okay, and this also breaks up as well. Now, remember when I told you about the definition that we're going to be forming bonds? Well, that is exactly what we're going to be doing. So this double bond actually does break because we've moved electrons, and therefore we're going to end up with a molecule looking like this, where we've got the bromine attached to the carbon, and we've got the carbon attached to two hydrogens. But if you've noticed, carbon always loves having 4 bonds, no more, no less. And seeing as we've got just only 3 bonds, it becomes it is a cation. Okay, that means it is positively charged on this end, and therefore, remember, opposites do attract even in real life. So we have the transfer of electrons because we've still got this bromine ion, this bromine negative ion over here, this anion. So we've got the pair of electrons are being transferred to this cation to make a molecule that looks like this, where we've got the bromine attached to the carbon, and now the carbon's got 4 bonds, so it's happy. Remember, this will be a dibromoalkane, not just a bromoalkane, and that's very important when you are naming it. So the next one is alkanes. Now, the thing is, it will not go through electrophilic substitution. Why? We do not have any double bonds. We don't have any rich electron center for anything to be attracted to it. So what happens is that we need to go through this process called halogenation, or over here, which is radical substitution. So say for example, I get a halogen, say chlorine, Cl2. We have to make a haloalkane. We need to make a chloroalkane. How do we do this? Well, there are 3 steps, and I'm going to go through them. The first one is initiation, where we have to split up this through a second means, because in the alkenes, it actually the electron center did that, but we don't have an electron center. So we need to have this lovely thing called UV light, and the UV light will split up the chlorine to make through homolytic fission, by the way, to make chlorine radicals. Now, if you think about it, I'm going to show you a picture of chlorine. So chlorine has 2 electrons which are being shared, which is quite right. And now when we break them up through homolytic fission, 1 electron will go to this chlorine, and 1 electron will go to this chlorine, meaning that we have got 1, 2, I'm not going to draw it out again, 3, 4, 5, 6, 7. Now we have got bonded electrons here, paired electrons, and we just got a single one, a single lone electron, and that's what this dot stands for. This happens on both of them, by the way. That's why we have got .Cl plus .Cl, okay? Or we can write .2.Cl, okay? So this is called a radical. So now, I've just written it out for you. Some people do write Cl dots like this. Again, it doesn't matter, just so as long as it's that it's close to the chlorine, it doesn't matter. So the next step is propagation, where we have this radical and it reacts with the compound where we actually wanted to react with in the first place. So we have got 1, 2, 3. We've got propane. I'm gonna have to draw it out. Propane is C3H8 plus the chlorine radical. Now what happens is that the electron, the lone electron, and only the lone electron will be substituted for the hydrogen. Okay, doesn't make sense? Well, the electron would go to C3H8 to make .C3H8, and then the hydrogen would leave, so it would make C3H7. Okay, so basically the electron has kicked one of the hydrogen out. It has substituted, it's been substituted, and therefore we've got a hydrogen plus and a chlorine minus to make HCl. Now what else happens is that we've got this second step, which is the .C3H7. Now it is important that the dot is before the carbon, because the spare electron is on the carbon and not on the hydrogen. So we add that with chlorine gas to make C3H7Cl, because what's happened is that this is split up and the chlorine has replaced the electron plus chlorine radical. So the reason why we do not have the radical plus another radical, even though that's technically what's happened, is because that is the termination step. Before we go on to the third step, the reason why we have this propagation step will happen over and over and over again. The chlorine radical does not stop. That's why when we go to resources, when we do this in module 4, you actually understand why chlorine is bad for the environment and many halogenoalkanes. So what happens is that we've got this happening over and over again, but for us to terminate it, we need 2 radicals to react together to form an organic or inorganic product. So say for example, we can have .Cl plus .Cl reacting together to make Cl2. If they ask you in the exam to write a termination step, that is the easiest one you can write. That is the easiest one, and you will get the mark. Unless it says do not include an inorganic compound, something like that. So for example, another termination step could be C3H7. So .C3H7 plus .Cl to make C3H7Cl. That's another termination step. And that's it. That's it for the termination. Now the last one, the halogenoalkanes or halogenoalkanes, we have got a halogen already attached to it. Now the reason why we would want to substitute, we do nucleophilic substitution, The reason why we would do that is if we want to make an alcohol, or if you just want to replace this with another one. So what we would have a nucleophile such as OH, where it is quite electron rich. It's got quite a few bits of electrons, and it attacks this nucleophile attacks a electron deficient species. Now you'd be thinking, well, where's the electron deficient species here? If you remember, bromine will be electronegative. It's more electronegative than the carbon. So that means what happens is that we go through a backside attack. I don't know why they call it that, but the reason why is because we go, I don't know why I drew it that far. There we go. All the way around the back. So we don't go through the front, we go through the back. For us to essentially knock the bromine out. That's exactly what we're doing. We're going to the backside and then kicking bromine out. So we would just basically end up with one of this, where we have the OH group, which has replaced the bromine plus the bromine ion, and that bromine ion will just float away, or it will just float away. So one thing I forgot to point out is that when this OH does kick the bromine out, we've got a transfer of electrons to the bromine. I can't fit it in, but this arrow should be further down, like so. Okay, and that is it for your mechanisms. Please remember, each one of those goes through one and its only specific mechanism.